Well, my name is Jeff. I'm the founder of the Earth Advocacy Project, along with my wife, Natalie. We're a new organization. We just got our 501c3 status back in May, so we're brand new. And I like to say that we fight environmental apathy. What that means is we work to get people involved and engaged in the environment beyond what they're doing already. My background is in public relations and communications, and Natalie is a psychologist. So our goal is to do things a little bit differently than most environmental organizations, and to sort of do our part to add some momentum to the environmental movement. This isn't all about us, so I'm not going to get into everything we do and how we do it, but part of our plan involves data, lots of data. Companies like Target, there we go. On button. Okay. There we go. Okay, cool. Thank you. Sorry about that. So companies like Target, Amazon, and Walmart, you have tremendous amounts of data that they collect on their customers. And they use it to analyze and predict behaviors and life changes for their customers. So that they can market to them when the time is right. There's a borderline creepy story about Target predicting successfully when a woman was about to become pregnant, or when she was pregnant, and in her second trimester, and so that they could start sending baby coupons. And they even do it for political campaigns. In the Obama 2012 re-election, they had a data science unit called the CAVE. The CAVE did all kinds of projects, but the one that I think is the most interesting, and the one that we're interested in, is this. They took voter registration data and matched it against consumer databases. And through the process of analysis and face-to-face and phone polls, they created algorithms that were able to assign a probability that each voter was likely to vote for Obama. 0 being absolutely unlikely to vote for Obama, and 100 being absolutely going to vote for Obama. They then focused on the people in the 40 to 60 percentile, figuring that those were the true swing voters. They focused their efforts on those people, and it helped them win the re-election. And my thought is, why can't we do that for the environment? Why can't we use these tools to analyze people's environmental behavior and predict who's ready to start acting for the environment, and when the time is right, give them a little nudge? It can be done, but it's a huge undertaking. I was able to talk to some people from the CAVE and some other data scientists, and the consensus is it can totally be done. It's not a matter of if, it's a matter of the resources necessary. And as a new nonprofit, we're short on resources. That is why this NewMet Data project is so huge to us. That's why the NewMet Data project is so huge to us, because we don't have the resources to do a project like this on our own. And, you know, we're able to find a group that's willing to work with us and will provide us actionable insights that we're really looking for. So let me give you a little bit of background on this. and why this project and how we're doing it and why it's important. In the late 1980s, California legislature passed a bill called Assembly Bill 939 that mandated that every community in California needed to divert at least 50% of its waste from the landfill by the year 2000. If they didn't do that, they faced a fine of up to $10,000 a day. So that means that recycling rates and diversion rates in California are really closely monitored so that they can be reported to the state so people can avoid their fines. And that data happens to be freely available online. So the bootcamp students are going to tell you more about this, but the important part is that we are able to look at each community and tell you how much they're diverting from the landfill, how much waste is being recycled, how much is being composted, how much is going to the landfill, and you know, if they're doing a lot, if they're doing more than their 50%, or they're just barely scraping by. Knowing what communities are high-rate recyclers and which ones are low-rate recyclers, we can then look at the characteristics of those communities and get an approximate idea of what sorts of communities and people recycle a lot and who doesn't. So we can get an idea of who is more engaged in the environment and who's needing a little nudge in the right direction. So by doing this, NewMet, jumped the gun there. So by doing this, NewMet has given us the ability to create a pilot project that we could never have done on our own. And the credibility we need to start pursuing bigger projects and more ambitious goals. So we're really, really grateful for NewMet Data. We've got a table in the back with brochures and in the e-newsletter sign up. My cards are out there. You can come by and find out more. You can check us out on the web. And now I'm going to introduce Mahmoud, one of the fellows, and he's going to tell you more about the project. Thank you.
Thank you, Jeff. Good evening, everyone. My name is Mahmoud Kamalzarian, and today my colleagues and I will talk about the project we did in the NewMet Data, and we'll share with you some of our results and findings. We will start the presentation by talking about the motivation and goals. Then we will show you the sources of the data we use for this project, how we clean the data, and a little bit about data exploration. We will show you some features and try to show you some insight of the data. And then each of us will talk a little bit about different models and algorithms we use to analyze the data and share with you some of the results we obtain. And we will have a brief summary at the end. For the motivation, I like to talk a little bit more about the Obama story. As you know, when Obama wanted to go for re-election, the unemployment rate was really high, and statistics said it was the highest value of unemployment rate in 76 years, so he was in a big trouble. The good things for him, the advantage that he had a team of about 50 data scientists called the CAVE, and this team predict the individual behavior of millions of voters, US voters, and the goal was simply re-electing the President Obama. They looked at different type of data sets, some of them like public data sets. They looked at the voter files, the census data. They also looked at some internal data set they had, like the field observation they had, also some internal polling they did, and some commercial data like consumers' data that they could collect. And using all these data and analyzing them, they were able to find the right group of people to be targeted by the political campaign to have the highest impact. Another interesting thing about their job was they were able to make a model that predict the election result with very high accuracy. You can see, for example, for Hamilton County in Ohio, the model predicted that about 57% of people will vote for Obama, and that was the actual amount of people voted for him. So we thought this story is very interesting. It was very inspiring for us. If they can use data science for political campaign, why not we use it for an environmental campaign? They try to find the right group of people to be the focus of their campaign, and here we have similar story. We want to find the right group of the right cities in California, the right group of cities that should be the focus of our campaign to have the highest impact. And it brings us to the goals of this project. We want to identify the key factors affecting the garbage production rate and also the cost of waste management. And the ultimate goal is recommending the areas or cities that they will have the highest likelihood to responding to the marketing effort of the client, the Earth Advocacy Group, and those where a response would have the highest impact. Before we go through the project, I want to talk about two terms that we use in this project. It will be helpful because you will hear them a lot. One of them is target trash production. Here you can see the equation is half of expected annual trash production, and it basically says states want each city at least recycle 50% of their total produced trash. And then the other term, which we will use a lot in this talk, is diversion rate. You can see the equation over there, but let me just explain it in word. It says the diversion rate is the percentage of the trash that either recycled or transport to some type of energy. So it's diverted from landfill, the percentage of the trash that didn't go to the landfill. So if we have a higher diversion rate, it means that we have higher rate of recycling. So if in the presentation we said a city has a diversion rate of 80%, it means that that city was able to recycle about 80% of their total produced trash. And in this slide, the x-axis is the years from 2007 to 2013, and the y-axis shows the diversion rate. And you can see the box plot for all the cities, the diversion rate of all the cities in California. And the red number started from 0.58 and end up to 0.67 are the median of diversion rate for all the cities in California. As you can see, the diversion rate, the median is increasing, but then after 2009 to 2013, it's almost at the same level. And again, it shows the importance and necessity of the project that Earth Advocacy Group is trying to do, and the project we are trying to do in NewMet Data. We want to find a way and find the right group of city to put our campaign effort on them and try to push this number moving up again. With this, I ask my colleague Suresh to come and talk about the data sources we use in this project. Thank you.
Hi, good evening all. My name is Suresh Nanjapan. I am here to talk about the data sources that we have collected for this project. And as you know, the data collection is the first step in the overall workflow. And I would like to thank our mentor who pointed us where the location from where the data can be extracted. Okay, so talking about the data sources, client wanted to know about the potential target of the cities and also the characteristics of the communities that can be targeted for the campaign. So to get those data, we thought of collecting the data from the Recycle website, the disposal and diversion data for the year 2007 to 2013, And the census data of, we have 4 categories, is the demographics, economics, social and housing. And that was available for years 2010 to 2013. And the political affiliation, and the last one is the retail costs. So the cost is for the trash, green, and the recycle. And we had limited data set because extracting the data for cost was difficult because it was available in form of PDF, and it was hard to, in fact, go and standardize the data because some of them were available cost per gallon, some of them cost per pound, and it was in different scales. Okay, so the data, as you know, it can be available in any format. It can be structured, unstructured, and semi-structured. And it can be available on the web, database, the file systems. For this project, the data was extracted from web, and the data was available in form of reports and data sets. The data sets meaning the files that can be downloaded. The data and reports, it was extracted using the web URLs and XML scraping for the data that was available in form of report. And we use the XML and reshape 2 packages and R. And the files, of course, it was downloaded. And then we combined all these data, the census, political, and disposal. And with the available data, we were able to get this years 2011 to 2013 after we combined the data. And this is one example. We can see the data that was available on the Recycle website in form of report. Okay. So just to talk about the features that were available in different categories, on diversion disposal, we extracted the data available on those websites were like county, jurisdiction, and the disposal amount, transformation rate, population, and employment. And on census, we had 4 different categories: the social, economic, housing, and demographic. On social, we had features like education, marital status, and relationship, etc. On economic, again, the income, employment, occupation. Housing, the structure, the cost, housing cost, and the utilities. And the demographics, it gives sex, age, the race on the housing units. On political affiliations, we got the voter registration and parties. And all these data were collected for all cities in California. So on merging the data, you can see the features that was available on disposal. We had like 31 features with 4 and 4 jurisdictions, that is also cities. On demographic, we had like 327 and 482 cities. Goes on with economic, social, and housing, and also political. And on the final data, we saw like 2,091 features with 12,000 plus observation with 341 cities. Okay, with this, I'm going to invite Amin to talk about data cleaning. Thank you.
Thank you, Suresh. Hello, everyone. I'm Amin Shabdakhani, and I'm going to talk about data cleaning and briefly some feature reduction. As Suresh mentioned, after we extract the data and merge them, we had a huge number of features, more than 2,000 features with 12,000 observations. So we started cleaning part with removing the features with too many NAs, as well as the features that have too many zeros. Also, we had some features that had no value in the feature or empty cells. Also, if a feature had a 0 or near 0 variance, we removed them from the database. On the other hand, we had to change the feature types. For example, we had to change some features from character or factors to numeric. Also, in some features we had them as a value, like population, and we had to change them to percentage to be comparable with other features. For example, if you had a political party affiliation and total registered voters, we calculated the percentage of each party. And finally, if we had a few NAs in each feature, we use the data imputation method to replace the missing data with a median or mean value. In the next step, we had to reduce the number of features we had. We started our work with the features that has too many detailed subcategories. For example, in the race category, we had a parent category like white, black, American Indian, Asian, and native Hawaiian. For example, for the Asian, we had Asian Indian, Asian Chinese, Asian Filipino, Asian Chinese, Japanese. We didn't use all of the subcategories. We just used the parent categories as the Asian. Also, if we had complementary features, like in gender, instead of using both features, we removed and just kept one of the features. If in some features we had too many beans for the data, instead of using all of the beans, we use the one representative features as a selection of that feature. For example, in income, we have too many beans. And also we had a feature like median income and mean of income. We just use the median income as a representative of this category. And also in the census data, we had too many features having them as a value, estimated value, and also the percentages. So we removed all of the values and kept the percentages. And finally, if we had a remaining NA, we used the complete case to remove them. And finally, as the most important part, we removed the highly correlated values using the correlation matrix. So this is the correlation matrix. It's huge. It's 800 by 800 matrix. As you can see by this color-coded bar, the variation of correlation varied from -1 to 1, and if we look at the one of the examples here, you can see for example, the high correlation between different features in the category of place of birth. For example, we have a native, and also we have a native born in the US. You see 99.9% correlation between them. So we just removed one of them and keep the parent category. Also, we see this high correlation between different categories. For example, we see a high correlation between the place of birth and language, similarly with race and other things. So we just kept we just removed the highly correlated values. In the next step, we had to reduce more features. So we used different methods to reduce the factors. For example, here we use the recursive feature selection, the RFE package in R, and we use the random forest method in this package, and we look at the root mean square errors, and we see how we see the importance of features here. So based on this method, we could select the highest and most important features. So using this method, we just received 53 features in total. Also, we tried other approaches like feature selector, and which include rank correlation, linear correlation, chi-square information gain ratio, 1R algorithm, symmetrical uncertainty, and also two other methods, the k-nearest neighbors and neural networks. As you can see in this graph, we have plotted a few most important factors, and in most of them, we see that almost all of the methods has selected them as a very high important feature. We plotted the features against the importance index, which is normalized by 1. And this was the feature reduction. I'm going to invite Jennifer to talk more about the data exploration. Thank you.
Up to now, we have collected the diversion rates data and census data. Along with feature selection, we also want to look at what the distribution of diversion rates and versus features before we make any decisions and conclusions. This is how we calculate diversion rate. It is almost equivalent to recycling. That being said, the higher the diversion rate is, the higher recycling there is. In order to distinguish jurisdictions with different diversion rates, we classified diversion rates into 4 classes, 4 levels. The highest level is the diversion rate over 75%, we call them excellent. Between the average 65% to 75% is good. Between the target 50% and 65% is fair. And those who not meet the target 50%, we call them low. In the right side in this histogram, we combined the distribution of diversion rates from 2007 to 2013. And we found that there is an obvious shift in the peak of all the distributions. That means on the whole, the diversion rate in California is increasing. However, in the recent 2 years, it is kind of on a plateau stage. And now it is time for us to work on this. Here is the distribution, geographic distribution of the diversion rates. Each dot here represents one jurisdiction in a specific year in the corresponding diversion rate level. In fact, in California, there is only a small number of jurisdictions which could not meet the target. The majority of the jurisdictions have done a good job. They have met the target and even done better. One of the purposes of this work is we want to push the dots here in this map here in this region. We want to push these dots into the right graph. And one approach to start this work is to explore the characteristics of these regions. And we do have the characteristics of these regions. We have census data, which covers different categories. We have social features like the education level of people, the language people speak in these regions. The economic category, we have the household income, people's occupation, how people commute every day to work. In housing category, we have the features of the structures in the buildings, the utilities of the houses. Also, we have the demographic statistics of people's sex, age, race, and also politics affiliations features. After we remove the redundant high correlated features and feature selection, there are around 70 important features left. Since we have a limited time today, so I will introduce some exploratory of some major features and interesting features. For instance, in the right graph, this is the plot of politics affiliation. The x-axis is the percentage of Democratic politics affiliation, and the y-axis is the Republican percentage. We use different colors to label the different classes of diversion rates. It is colorful, and there is no strong correlation we see here in this graph, except in a few areas there will be some similarities here. Here, these three graphs are the plots of diversion rates with three features. The y-axis here is diversion rates, and the three features here is from left, this is the number of waste diversion programs implemented in this area. In the middle, this is the median of the population age in the area. And on the right side, this is the median of the buildings built year in this area. Although we didn't see strong linear correlation among these three features, but we noticed that here in the plot of diversion rates and age median, we found that the areas with more young residents live, there might be a lower diversion rate. And here in this plot, the year built median with diversion rates, buildings built in 1960s and 1970s might be related to a relatively lower diversion rate. Next, we extend our exploratory to more features. Their language people speak, education levels, people's commute to work. The y-axis is diversion rate, and we also use 4 colors to label 4 classes. From the top to the bottom, it is excellent, this is good, fair, and low. Each graph represents one feature, exploratory. We notice that the education level of population may have some impact on this. Here in this plot, we found that where there are more people with an advanced degree, graduate degree, they might be related to a higher diversion rate. Adversely, in this plot, where more people with less education, the diversion rate is relatively lower. And in the commuting way, we found that when more people take public transportation, it may be related to a higher diversion rate. We also look at other features like the people who work in different industries. We notice that if there are more people work in agriculture, we found that this could be related to a relatively low diversion rate. This is a plot of utilities, that is mainly the heating system used in a house. We found that the usage of wood as a heating fuel may be related to a relatively low diversion rate. And this is a brief introduction of the data exploratory. And next, we will use machine learning and different models to work on the data in hope to gain more information for our campaign. The first model I will introduce is random forests. Random forests has higher accuracy among current algorithms. It is good for a large number of features, and also it can estimate the importance of variables. Here we use a package called carrot in our language to apply this method on our dataset. Data is spliced into training dataset and testing dataset, and we use the random forest method. In this table, it gives the prediction of the testing dataset. It gives a pretty good prediction. And this list gives us the top 20 important features within this random forest model. These important features include the industry infrastructure of the cities, like agriculture, manufacturing, transportation, etc. Also, the education level, like people with associate degree or any other degrees. And also, it covers the number of programs implemented in these areas, and the electricity, the heating fuel people use, and the year built, the median of the year built in these areas. But one of the cons of random forest model is it is hard to interpret the results because it is hard to examine each individual tree in the deep forest. And we applied many other more models. Now I will introduce my team member, Toga, to introduce his model.
Thank you. My name is Tolga. So I tried to implement the social network analysis model to see how that would work with this data that we have. The main reason why I tried this approach is because we had diversion data from 2007 to 2013, but once we combine it with the other data sources, we lost almost all the years except for the last 3 years. So I didn't want to lose that much information, so I was just thinking, what can we learn just by looking at time and the location of the cities alone, and nothing else? So just looking at those two things over the last 7 years. And the main idea is, if you have neighboring cities who reach the 65% diversion rate goal, is this going to put pressure on your city to also divert? So are you basically affected by your neighboring cities or not? And if you are affected, how does this play out in the long run? And I got this idea just by looking at these maps. So again, as was pointed out before, each dot is a city. Green ones are those who are doing okay. They're doing well in their diversion rate. And red ones are doing poorly. The darker the red diverse it is, the darker the green, the better it is. So this is the first year we have data on, 2007. And right after, we see a lot of greens invading the map. And then it kind of slows down, but over the years, you see more greens than reds. So it's definitely spreading. So I just want to see how it spreads. And can we use a network analysis model to model this? So adoption, what I call adoption is when a city didn't have 65% diversion before, but in the next year, they have 65% or more. So then they have adopted a good recycling habit, let's say. And it can happen in two ways. It can be spontaneous or peer pressure. Spontaneous is basically when you adopt, even though none of your neighbors have adopted before. And peer pressure I call when you adopt, at least one of your neighbors had already adopted. So that means you are affected in a way from your neighboring city. And I'm using a model, this is not my model, and if you're interested, I can lead you to this paper. So this is not my notation. Okay. Again, when you're building a network, first question is, what is an edge? What is a neighboring city? How do you find? So what I did, I kind of tried different ranges from 1 kilometer to 25 kilometers. And so which one correlates most with the prediction? So we held out some data and made predictions. And the highest correlation was for 15 kilometers. So this is kilometers on the x-axis, and this is the correlation for the held out data. And 15 kilometer was the highest correlation. So that means in the model, if two cities are 15 kilometers within each other, we call them neighbors. There's an edge between them. If they're further apart, they are not connected. And I use kilometers because everybody should use kilometers, in my opinion. So this is how the network looks when you put those edges in. And again, greens invade after a while. So how does this peer pressure versus spontaneous look like? The spontaneous is again when your neighbors do not adopt, but you decide to adopt on your own. It's low and it's pretty much stable over the years. Whereas peer pressure is again, at least one of your neighbors had adopted already, and then in next year you start to adopt. And that is a higher percentage, but also it increases a lot in 2008 to 2009, and then kind of slowly goes down, but still it's always higher than the spontaneous. So there's some difference between spontaneous versus peer pressure. So there might be a network effect. So let's break it down even further. So now I break down peer pressure into subcategories. What if 80 to 100% of your neighbors adopted? What if only 60 to 80% of your neighbors adopted? Only 40 to 60, 20 to 40, 0 to 20, and black is just spontaneous. None of your neighbors adopted, but you decide to adopt a good diversion rate. And there's a nice ordinality here. The more percentage of your neighbors adopted, the more likely that you will adopt. So the red is always above the others. And this kind of logic pretty much holds over the years. So the more your neighbors have adopted, there's a good chance that you will adopt. And this kind of was the idea behind this model. So then we made a projection what it would be in 2014. Again, it's very low. It's stabilized, as people already pointed out. So there's not much chance for adoption anymore. It's kind of dying out. But still, we expect cities whose neighbors adopted to be more, they can easily change their attitude maybe. And those are 19 cities. Here are their names. So these have cities who don't have 65%, but most of their neighbors have 65%. So they might be good candidates to focus on. And here's how they look on the map. We classify them into two. Red ones are doing really poorly, and then the pinkish ones are more than 50%. So we look at them separately, and here are some characteristics of these. The one on the left are the ones who are doing really poorly, and the ones on the right are doing relatively okay. 20 to 30% Democrats versus more than 50% Republicans. So mostly Republican cities, predominantly white, 80%. And these are poor cities, I would say, I guess, 60%, again, more than 50% are making less than 50K a year. They don't tend to carpool. They're mostly using car, and they're using it alone. So these are some of the characteristics. We have more, but these are the most interesting ones. And I think that's all this model has to say, and I'm going to now give it back to Mahmoud for the time series model. Thank you.
Hello again. So I'm going to talk about another method that we tried. It is called time series. The reason that we tried this method is by now we all know that diversion rate, which basically is percentage of recycling, is different from one city to another, and even for one specific city, it's different year by year. So we said, so for example, we have cities like Chochila that you can see their diversion rate is improving year after year. We have some other cities like Kolinga that they did a good job in 2010, but after that, for some reason, their diversion rate just decreased. And then some cities like San Diego that their diversion rate is almost at some level, and it just fluctuates around that number. So we thought, why not we classify the cities based on the diversion rate change, and then use the model to predict what would be the diversion rate change in the next year. For example, that's the idea. If we have a time series of the diversion rate for a city, we give it to the model and it tells us what will happen next year. We use supervised classification for this part, and we define three classes. The first class is the worsened cities. These are the cities that their diversion rate from one year to the next is decreased more than 2%. Then we have the second class, which is no change class. And these are the cities that their diversion rate maybe just fluctuate a little bit, less than 2% up or down. And then the last class, class 3, are those cities that the diversion rate is improved more than 2%. We use 75% of the data for training, and then the remaining 25% for testing the prediction. For supervised classification, we looked at what are the algorithms that people think are the most, the good one, the significant ones for supervised classification, and we explored a couple of them. For example, one is diagonal linear discriminant analysis. We use SVM, k-nearest neighborhood, and also random forest. In the second column, you can see the packages that we use for this algorithm, and the last column shows the accuracy of these methods to predict what would be the diversion rate change for each city next year. We also have the random method. It means that we just randomly assign a class to a city, and you can see that the accuracy of the above four methods is higher, especially SVM and K nearest neighbor has higher accuracy. So it looks like that in the first look, it looks like that SVM and K nearest neighbor perform okay, but then when we looked at the confusion matrix, we can see that none provides promising results on predicting what would be the diversion rate change for the next year. So if you look at the rows, the predictions, you can see that the methods try to put all the cities in the middle group, the no change group. So basically, if you provide the city to the model, it would say that next year you will have the same diversion rate. Here you can see the list of some of the factors we think that maybe can explain why the methods doesn't work well. One of them is there is a lot of fluctuation in the diversion rate, especially in the last 3 years that we use for the time series. So we have cities with very different characteristics, but all of them kind of goes up and down, and there is not a very clear trend. So it may confuse the model. Also, we think maybe even for a small diversion rate change, maybe there is something happen in the city that can explain that, but probably we don't have that feature among the features we use for this super-wide classification, so maybe we miss that feature. And also the last thing that I think is very important is we just looked at 3 years time history, and when you want to do a time history analysis, it's very short. And probably if later on when we have longer record, we come back and revisit this method, maybe we will have more promising results. So we thought that although this method didn't work very well, alongside the other methods that results to very promising answers, it might be a good idea to show you some of our trials that didn't work. Okay? So I'll stop here and pass the podium to Mahdi for the next part, which is clustering. Thank you.
Okay. Hello everybody, my name is Mahdi Nawari. So I did the clustering for this project. So when we say clustering, so when we have unlabeled data, the first approach comes to my mind is do the clustering. So the basic idea for the clustering is to find a group of objects where the objects within the group are similar, but the objects between the group are totally different. In the context of our project, so we are looking at the group of cities which have a similar characteristic. For example, they are similar in terms of the social, economic, demographic, and also political characteristic. So, and then we try to answer this question, is there any relation between this group and diversion rate or not? So, first question is, what is the best number of the cluster? So when we are doing the clustering, so how many clusters we have to use to cluster the data? So there are two common methods for to identify the number of the cluster. The first one is a script plot. In the script plot, you can see the number of the cluster in the x-axis, and the y-axis is the square distance between each member in the cluster and the centroid. So, and normally we have an elbow-shaped graph in the script plot, and the point close corresponding to the elbow is the best optimum number of the cluster. But as you see, in this case, we couldn't find any elbow in the graphs. The other method is to use the silhouette plot. So in the silhouette plot, we tried it for the different number of the cluster, and we find the 4 cluster is best fit in our data set. And as you can see here, you can see what's the silhouette widths represent how well each object fall within the groups. So for example, we have an average silhouette width of 0.74, which shows a strong structure have been found in this data set. So knowing that, we apply the k-mean clustering, and we use the 4 different clusters. And in each graph, you see the cities versus diversion rate. And you can see in the first cluster, we have all type of cities. We have cities with a very low diversion rate. We have cities with a fair diversion rate. We have cities with a good diversion rate. And we have cities with excellent diversion rate. For example, in this group, you see just 2 clusters. The cities with the good diversion rate and cities with the excellent diversion rate. So if you look at the next plot is almost similar to that one. Here, each dot represents 1 city, and also the color code is the same as the color code in the previous graph. So again, we have a different cluster number 1, 2, 3, 4, and we have a diversion rate in the x-axis. Here we have 2 strategies. For example, we can set up the different campaign to improve the diversion rate, which it can work, for example, for this cluster. This cluster, these cities in this cluster, they have already good job. They have a good diversion rate and they have an excellent diversion rate. But if you put some campaign, maybe we can improve the diversion rate in these cities and move them from good to the excellent. The other strategy can be to, if you look at this cluster, you see all of the cities in this cluster have a very good diversion rate. But these 3 cities, they are some kind of outlier. So why is happening? So we can ask the mayor or city official. So your city, in terms of the social, economical characteristics, are very similar to the other city. Why your city is not doing well? So this is another approach. And also we can go 1 level deep and see, okay, what's the characteristic of this city? What's this city have in common? If you look at this graph, you can see, for example, the cluster number 1, which was this cluster here. And the red bar shows the cluster number 1. So you can see the median of the building has been built is larger than, so we have a newer building in this cluster. So the public transportation, the people in this category is willing to use the public transportation. In terms of the median of income, this cluster has a higher income in comparison with the others. In terms of the labor forces, we have a more population in the labor forces. So the mortgage is the higher, and also these people in this category less likely to work in the governmental job. And also they are a younger generation because many of them have children under 6 years old. And also in terms of the education level, you can see that more people in this category have an associated degree. And also in terms of the recycling program, they have a more number of the recycling program in these categories. So this is our approach using the clustering method. With this, I am going to invite my friend Suresh to explain about the support vector machine. Thank you.
Hi, back again. I want to talk about the model SVM, which is used for classification. Before that, I would like to state, I look at data science is more of used in the business, identifying the business opportunities, improving the operational efficiency, and provide some actionable insight to business to make a better decision. So that I would like to continue to other models. Okay, so SVM is support vector machines, which is used for classification. And the reason we use is we want to analyze the results with the different classification and also get the class probability estimation to predict cities which are likely to respond to EAP campaign. For that, we took the target or dependent feature diversion rate and classified into low, fair, good, and excellent. We use the packages E1071 and Caret for the SVM and the confusion matrix, and we use the Tableau for doing the visual exploration. Okay, so I just added more reasons why we use the SVM. So SVM tends to be less sensitive to outliers, and it incorporates complexity control. So when we say complexity control, I think it's more of trade-off between the bias and the variance. And outliers, what can be outlier in this data? So I just put the alien. And also we think SVM, the penalty for misclassified point is proportional to the distance from margin boundary, and if possible, SVM will make only small errors. So as you can see, this diagram, this is an outlier, and the other classification will try to fit this, and SVM will be less sensitive to the outlier. And also you can see the margin around the separation in SVM. So these are the results from SVM. Like we have confusion matrix, where we have prediction versus the actual. So how many of the low ones were predicted as low versus fair, and also the other rest of them. So the idea behind this is we want to identify the target cities if the prediction gives a different result than the actual one. So the statistics, you can see the accuracy is 87%. And this was trained on 98 features and 928 observations with 314 cities. And again, it's from the combined data set from 2011 to 2013. So these are the results from the model. And we think that these are the target cities are potentially targeted. And this is the, you can see these cities, we are saying this is the actual class where it was fair and the predicted was good. And the probability of these cities going from like fair to good is like 59%. So this one gives the result with the targeted cities with the probability that it can potentially go to better diversion rate. Okay, with this, I'm inviting Zeka. Thank you.
All right, logistic regression was the model that stuck out in my mind right from the get-go because of its continuous prediction ability and its ability also to detect directional changes given inputs. I also wanted to explore costs associated with a predicted minus an actual that related to different categories to try to see how people were responding to cost, how it was affecting their behavior possibly. So again, it allows for expectation of directional outcomes and gives interpretable coefficients. In the log odds world, that doesn't always make sense, but you can basically boil it down to something such as, given a 1 unit change in X, say population of a certain demographic, we're likely to see an outcome of Y. And it also gives significance in that regard. It fits the diversion rate curve continuous, as I said, and it uses this as a proxy with our diversion rates in place of probabilities. We use a binomial type of model. The key I can actually look here. The key outcome again is predicted minus actual diversion rate differences, and in finance we refer to this as the spread, the plus or minus of a distribution. We blend the spread again with trash volumes, prices, and median incomes per place to try to give us more bang for our buck. We really want to push the nudge factor here. All right, so positive impact is really what we're driving at. And I've been going through this the last couple weeks trying to find a way to boil down a very limited data set of trash costs and trying to standardize it in such a way that would make it interpretable and easy in the context of this continuous model. And also, as data scientists, we've been told over and over that in large organizations, A/B tests, hypothesis tests, distinguishing the true difference between two populations, given a control in a scientific experiment, is something important. So I'm looking at this in the context of observational data, which is social and highly changeable. How do we apply that to a scientific method? But first, how? This model doesn't get fancy in terms of, we don't get fancy in terms of choosing a way to select per se. Stepwise selection is what was used with 800 variables. It's using 1 year. In sample, it did very well. Out of sample, it also did very well with a 94% accuracy out of sample with a 40% held out. 12 features were finally chosen using this automated approach of selection, which was new to me. It was a good experience. And now linking it to the potential savings. So the logic here is to extend the good recycler as the green recycle logo and the red the bad, the A group and the B group as the euphemistic good recycler, bad recycler. Because in a sense, we're all good recyclers. We're always improving, but we've stagnated as we discussed as teams. We're seeking, in a test sense, to target these areas where we are basically measuring whether or not one will be the good or one will be the bad. And the A/B test will prove this. But we have a limited budget. So we have to always consider, how many people are we going to poll? How often are we going to poll them? And we have to be very sensitive to that. We're seeking the success where the bad recyclers are in fact changing given this predictive model. So here we see on the x-axis California places sorted by the diversion rate, and you'll see a red line all the way through. This is sorting diversion rates in 2013 among 312 census places. On the line, black dot line area, you'll see, they're just connected by a line arbitrarily. You see particular points that fall plus or minus below this actual point using the logistic regression model. Here are good recyclers and our bad recyclers in a relative sense right now. So we have bad recyclers, quote unquote, predicted to actually divert more than they are, especially where the spread is wide. And the reverse is true with the green. When we extend this into cost, it's important to note that price does play into the relative good recycler and bad. On the x-axis here, we see that spread starting with 0 up to 40% spread, where these outlier cases, if you will, predicted outlier cases, fall into these two zones, general zones. And it was interesting to me that you almost had a 30% correlation with the cost of recycling increasing when people were bad recyclers throughout the state in 2013. They were, there was a correlation, positive correlation with the disposal cost per gallon for recycling. So people are being disincentivized to recycle effectively. Those that should be recycling more, given their significant coefficients, are in fact being disincentivized. Up here, these is your green, your compost, and etc. They're paying a lot, but in fact they're not capturing this potential up in this area when they could be saving money. That could also be due to size effect of a city, which we'll explore at a later point. But what I wanted to really do, back to the nudge and back to the powerful incentives, we took this model and extended it out to annual expected savings, percentage of a median income, and weighted it toward the actual volume of trash in different categories, blending both the recycling volumes per year and the green waste volumes per year. And what we see is so this is sorted, but we see where our true candidates really are. On the y-axis, these people here could save up to 0.5% of their annual income, adjusted for their median for the median salaries of that year in these areas. Eureka, Sacramento, Hayward, lots of bang for your buck. These people are recycling because they really like to, or so I think. So I'm going to transition into the summary and try to synthesize my point, but also the point of all of the other teams, groups, and individuals. Quite a hard task, we'll give it a shot. So we find that in certain places, people are more influenceable. Tolga pointed to this in his model on influence specifically. SVM as well, random forest, all of them did. So we aggregated that and looked at the logistic regression model and others to try to narrow those down. Eureka, Sacramento, Hayward, and Daly City, lots of positive impact potential. That's a consensus at the moment. This list could be extended out depending on how much it wanted to be. So we're targeting places emphasized by important socioeconomic features. If we want to do this, you can do this. A campaign can be targeted based on that. And again, A/B tests and other types of tests can help measure and scale. On the right, this map stood out. I didn't quite know where to place it. It's a map of different contaminated well sites throughout the state. So you see, reaching all the way from Los Angeles all the way up into the north, hundreds of contaminated wells, drinking water wells. So water quality, this is not a doomsday scenario, but water quality is certainly an issue, and it's also an issue in my own experience with trash facilities. Water you can have waste seep into the water system. Bottom line. Future steps, we would like additional socioeconomic features extended across different categories and time. Costs and volumes from private entities would be nice. Only 50% right at this time we can get more retail costs related to different recycling types and waste types. We also want to explore additional models, as we've all agreed on.